doing, as far as doing the computations. Okay, that's important. So let us move on a little bit. So what is a group? I hope we have kind of experience with that now, given the examples we get through. It's basically a set, it's not empty, where we have a way to combine the elements that behave well. Put two elements together, still in the set. The way you put them together is associative. There's an identity and inverses. So here's the first kind of result, if you will, about groups, propositions. Let G be a group. So there's only one element in the group that behaves like the identity. Any ideas on how to prove this? This is one of those proofs that I almost feel slimy when I'm done. I want to show that there's only one identity, right? Why don't I assume that I have two identities and show there only has to be one, right? So let's try that. So let me recap what this means. This means EX equals X, E equals X, for all X, B. So it needs to be an identity, but this also must be true for F. Now, this is so silly. E equals EF because F is an identity. But now EF is equal to F because E is an identity. Right? And don't feel kind of silly. There's only okay. Okay, so here's here that's useful along these lines. And suppose that's why our elements in the group. Number one. What do you suppose the inverse of X is? I would hope, right? And number two, what's that one is? Oh, you didn't trip up. Good. So you challenged a little linear algebra there, right? This is actually line inverse. So let's prove these. First, I'm gonna show something. This is part of the wonder of proof. Now, I'm gonna actually do something in this proof that says more than what I put in the result. Proof. Claim that if X is T, then the inverse is unique. We know that every element of a group has an inverse. Why? Because we said so. That's one of the things we assume when we're talking about a group. Everything's got an inverse. I'm gonna take a step farther. Not only does X have an inverse by definition, but that inverse, there's only one. So let's suppose it's very similar to the last attack that we had on the identity. Let's suppose we have two inverses and show that they're the same. So let me remind you what this means. This means that XZ equals CX equals the identity and XY YX. So both X and Z function as inverses. Any ideas on how we could? Right. So from this, now multiply both sides of this by, actually it doesn't matter, Z. Super careful. These two are the same, so if I hit them on the left by Z, it should be the same, right? Now I'm gonna use the associative property. Associative property says I can do this in any order I want, I'll move parentheses. And what is ZX? It's the identity. But this is the identity. So Z. Well, you gotta be, you're assuming you can cancel, right? So in fact, even in the integers, you can't always cancel. Let me show you an equation that will anger your blood. 2 times 0 is 17 times 0, right? But you can't cancel the 0, right? And so what we've essentially done is we've justified what you wanted to do. We've shown essentially that you can cancel in the group. That's essentially what we've shown. Okay, so now let's get on to the meat of this. So the inverse of X inverse this is the identity of G, because what this says is here's Fred and here's the inverse of Fred, right? That's what X inverse means. This is the identity, right? And it doesn't matter what side I put that on, right? Same. This is also I agree with that. So, both x and x inverse function as inverses to x inverse. Right. Now, I should be a little bit more careful here because really to be an inverse, it's got to work on both sides, right? But you can check me that it doesn't matter what order I put these in, it's still the same. Hence, both of these things function as inverses to x inverse, but that statement shows that any inverse is unique. So since x inverse inverse and x, both are inverses to x, they have to be the same thing. I'll do the same thing right here. And I'll be careful with both directions on this one just to show you. Let me point out that I just want to do this multiplication. I can bunch those parentheses like that. Great. Let me check it on the other side. Now, instead of multiplying this thing on the right, I'm gonna multiply on the left. Check that. This is y inverse, x inverse x, because I can put the parentheses wherever I desire. So y inverse, x inverse functions as the inverse of xy. Because when I multiply by xy on either side, I get the identity. So xy inverse, y inverse. Questions on that? Oh, this is one of the coolest theorems ever. Let's see. Do I have tools required? I'm sweating. So that just means the number of elements in G is some defining number. A group with 10 elements or 43, whatever you like. If X is in G, then there exists M in the natural numbers such that X, is definite. This is a cool theorem. By the way, what do I mean by XM? That means X to the M just means I do the operation to itself a certain some M number of times. That operation could be addition, it could be multiplication. I bet if you think about some examples, you remember the example Z mod n, let's say Z mod 12, where you take the number 0 to 11 and you add them up mod 12, right? So 1 plus 1 is 2, but then 10 plus 10 is 20, which should be 8, right? Every element has finite, well, has this property. Take 1. How many times do you have to add 1 to itself before you get 0? In Z12. 12 times. You add 1 to itself 12 times, you get 0. How about 2? Times you have to add it to itself to 0. What's the smallest number you can get? 6, right? If you took 4, you don't have to add it to itself 3 times, right? But any of these work. This is why, do you all remember me doing the Rubik's Cube example and I just kept turning, poof, after a while it solved? That's what this theorem tells us has to happen. Right? What did I do? I did a little twisty, right? And this little twisty on the Rubik's Cube is an element of the group. And I did it over and over again. The Rubik's Cube has an enormous number of combinations on it, but it's still finite. Right? And after a while, I was guaranteed this would come back. But this is an amazing theorem. It's an amazing theorem. You can't, if you have powers of X, say, if you're doing X to itself, it can't just go around in a circle. It has to come full circle back to the identity. Why is this true? Let's see if we can prove this. This is an example there. Yeah, here's a strategy on this. How might we go about this? Well, the first thing I do, I always got to have courage to write something down, whether it's going to work or not. So let's look at this. You know what? I'm going to make a list. And I'm going to do that for you. The first element is X, the second element is X combined with itself. The next one is X combined with itself 3 times, and so on. I was too lazy to write it all out. That is an infinite list, isn't it? Right? Because I'm going to write down the power of X for every natural number. That's an infinite list. Is it an infinite set? It cannot be. How can I? G is fine. Never list of X. But it's fine. And what does that mean? What conclusions can we make about the list if G is finite? Can everything on my list be different? Right? If you look at that list, X, X squared, X cubed, X 4, forever and ever and ever, it can't all be different. Right? Because all of these are elements of G, but there's only finitely many. So, what is the simplest conclusion you can come to if you know they can't all be different? Right. And in fact, I'm going to go economical on, and I'm going to say there have to be at least 2 that are repeated. In fact, a lot more than that, if you want to. But Let me be more precise. That is, there exists in A, in the natural numbers, such that x to the n is equal to x to the n plus n. That is to say, on this list here, after a while, we get to x to the n, and then later on in the list, we get x to the n plus k, and we see it's repeated. Right? That has to happen. Let me point out that, let me write this way. This is combining x with itself n plus k times, this is combining it in with k, right? Now, what do you know about a group? Everything's got an inverse, right? In particular, x to the n has an. This is often written x to the minus n, but it's even easier for me to write y. So let's multiply this by y. What's y times x to the n? It's the identity. And that's going to be the identity times x to the n. So look at what this tells me. And that proves right there that if you start with a Rubik's Cube that is solved and you do any kind of crazy move to it you want, write it down so you don't forget. Maybe it's 7 steps, then you repeat that 7 steps, and then you repeat it again and again and again and again. Eventually, the cube will resolve itself. So, let me give you a definition here. I'm going to use definition / notation to go with this. Uh, 6.113. In a group. Now remember, G is first and foremost a set, it's not empty. It's just count the elements in the group. That's it. Yeah. It's an element. And of course, my natural number here does not include 0 because in group theory, you take x to the 0 power to always be the identity. If there's a positive power of x, that is the identity, then we say that x has 5. And if x has finite order, the order of X is smallest. It's the smallest K in the natural numbers such that X to the K is the other. So let's look at an example here. 18. Okay, I want to, this is a group of finite order, 18 elements, right? Where we do the addition the way you think we would do it. 6 bar plus 6 bars, 12 bar. Somebody tell me what's 11 bar plus 14 bar? What do you think? So 11 bar, so I'm going to say. What did I say, 15 bar?
Oh, you said.
So where should that be? 7. Good. This is 25 bar, so I can divide 25 by 18, remainder 7. What are the orders of the elements? There's one element in order 1. What is that? Yeah. How many times do you have to add it to itself to get the identity? Just once, it's already the identity. Are there any elements of order? Well, so somebody find me an element of interesting order, and then we'll find all of it. What's the order of 2? Well, actually, how about this? What's the order of 1? How many times do you have to add it to itself to get the identity? 8. Let's see if we can find all of them. Then we've got something in common. You gotta add it to itself 18 times. You get that. Notice, if you add 2 to itself 18 times, you will also get the identity. Right? Because if you add 2 to itself 18 times, you get 36. When you divide by 18, it's got a remainder 0. But can you do better? What is the order of 2? What's the order of 3? Right? You had 3 to itself, so that works out real nice, right? Because these are all divisors. What's the order? Does 4 divide 18? No, it doesn't. It does divide 36. Right? So you have to add 4 to itself 9 times 36. What's the order of 5? It's 18. You seem like you picked up on that pretty quickly. Can you tell me something about 5? Because why its order has to be 18?
It doesn't divide 18.
Something's right, but neither does 4.
And it's probably the greatest common practice.
The greatest common divisor is 1. So to ramp up, to get a factor of 18 in it, you actually have to add it to itself 18 times. What's the order of 6? How about 7? What do you think? It's also 18, it's relative to 18. 8. This is also 9. How about 9? Okay, so let's kind of fill out the rest of this. What about 10? That should be order 9. 11 should be order 18. How about 12? I think 12 should probably function like 6. I should have order 3. 13 is relatively prime to 18. 14, that's 2 times 7. It should function like 2. The 7 is relatively prime. 15, that's 3 times 5, and 5 is relatively prime, so it should function like 3. 16, that's 2 times, well, that just shares the factor of 2 with 18. So should be order 9 as well. And 7. What's the order of the group? The entire group itself, how many elements are in it? 18. Do you see anything in common with the? Do you see any connection between the order of the group and the order of the elements within it? It seems to be true. Right. See a connection there? Can anybody give me a relationship between the order of the group, which is 18, and all the different orders we found of the elements in there? That's right. The order of each element divides the order of the group. Right? I didn't find any elements in there of order 4, or order 6, or order 7. They all had to be divisors of 18. This is not a coincidence. We will prove that this is true later. Be careful. In this example, every divisor of 18 has an element of that order. Right? This, on the other hand, is not true. Just because you have a group and it's divisible by a certain number doesn't mean there's an element of that order. But the element of the order has to divide the order of the group. It's finite. What is true is if you have a group, there will be an element of order P for every prime dividing. But that's for later. By the way, when I talk about a group being of infinite order, that just means it's got infinitely many elements in it. If I say that the order of an element in a group is infinite, that just means that it's not a finite order. Can anybody give an example of a group and an element with infinite order? It might be easier to think. I bet you'd have to give me an infinite group. Yes, that's, yeah. In fact, the rules under addition, no element has finite order except the identity. I want to give a smaller example. Like I said, the identity always has order 1. That's true in any group, right? Take any integer that's not. This is true for any integer that's not 0. How many times does it take me to add up 1? How many times I have to add 1 to itself and get 0? Your silence is correct. You can't do it. You add one and one and one. It's never zero. One is of infinite. Okay, so now that we've kind of broken ground, let's look at. Get some subgroups and homomorphisms. So. What do you suppose a subgroup is? Well, subgroup is just a baby group inside a parent group in a certain sense. So. But G, and I'm gonna write its operation down for the purposes of this definition. So suppose that I have some group G with operation circle. And let's say that H is a non-empty subset. Well, we say the non-empty subset H in D is a subgroup if so for example, so a subgroup is just a subset that has is itself a group. Okay, let's look at Z6. So I didn't want to do Z18, so I'm big for this. Let's look at Z6. This is a addition, this time mod 6, right? So 4 plus 4 is 2. Let's see if we can find all the subgroups. Any ideas? There's two cheap ones you can always rip off. Here are the smart aleck subgroups. Right? I mean, that's kind of stupid, but it is technically a subgroup. It's a subset. So, what's the other extreme? There you go. Good. Zero is also a subgroup. Close under a dish right, 0 plus 0 0. It's very so. But there are others. By the way, how many subsets does C6 have? Just subsets, forget subgroups. It's kind of a good reminder, maybe. 2 to the 6. This has got 64 subsets. Most of these subsets are not subgroups, right? In fact, to be a subgroup, it's necessary that it contains 0, because you always have to have the identity, right? And containing 0 is not good enough. If I took the set 0 and 2, would that be a subgroup? What's wrong? 2 plus 2 is outside of that set. So in fact, this gives me a little inspiration. Maybe what I can do is just, so is there a subgroup that contains 0 and 2? This ain't good enough, because the problem, as was pointed out, is once you've got 2 in there, you got 0 plus 0, you got 0 plus 2, but you also need 2 plus 2, which is not there. So let's throw that in. How about now? This one actually is, isn't it? Add these two, add this to itself, you get this, add these two, you get 0. In fact, these two are inverses of each other. This is a nice little closed subgroup. There's actually one more subgroup.
see. No,
Just do zero.
This one. That one's a subgroup by itself. It's 3 plus 3 is 0. Right?
are there any more? 0, 1, 5.
If you've got one, what else do you have to have?
I see you need that.
Right. In fact, if you pick up one in any subgroup, you automatically get all the rest of it, right? So once you've got one, you need 1 plus 1, then you need 1 plus 1 plus 1, and so on. The same thing happens with 5, right? So, but there still might be. Well, what happens if I have 2 and 3? What happens if I have a group that has 2 and 3?
You have to have 5 in it.
This takes us back to the first one. Let me point something out. What is the greatest common divisor of 2 and 3?
1.
Everybody agree with that? 1 is the greatest common divisor of 2 and 3? And what's the big thing that we know about the greatest common divisor of 2 elements? It's a linear combination of those two. There exists n m in the integers such that 2n plus 3m is equal to 1. Let's do a translation to see 6. What this says is if you have a subgroup that contains 2 bar and 3 bar, then adding 2 bar to itself n times and adding 3 bar to itself n times will give you 1. So 1 has to be in the subgroup, so it has to be the whole thing. In fact, I can go a step further, not just 2 and 3, but if you have any 2 elements whose greatest common divisor is 1 that are in the subgroup, it has to blow up to the whole group. You can use that to show that this is it. Notice the order of the group is 6. There is a subgroup of order 6, subgroup of order 1, 3, and 2 for every divisor. It turns out the order of the subgroup has to divide the order of the group. We'll prove that later. But just because a number divides the order of the group doesn't necessarily mean it's got a subgroup. There are counterexamples to this. Also note for this example, there's one and only one subgroup of that order. You all remember this notation from last time? Right? Like, first is the identity function that leaves everything alone. The first function is it swaps out 1 and 2 and leaves 3 alone. Swaps out 1 and 3 and leaves 2 alone. This one cycles, takes 1 to 2, 2 to 3, and 3 to 1, so forth. This one is a little different. Here are the subgroups here. So you should verify this. Verify these are all subgroups. Always, the whole group and the identity will be subgroups. There's one subgroup, order 3. There are actually 3 subgroups. Also, these 3 are subgroups. This begs a question too, by the way. The order of 6 is 6 and the order of 3 is 6, right? These are very different groups. Can somebody give me something really striking that's different about these two groups.
Number of subgroups,
I'm sorry,
the number of subgroups.
that certainly, he's correct, right? One of them has 3 subgroups, or 2, one of them just has 1. But when you combine things here, does order matter? 2 variables, 3 variables, 3 variables, 2 variables, same thing. Order doesn't matter. Order does matter here. Right? In fact, I'll show this dramatically. If you look at, this will be a kind of reminder. This, let's see, what is this? 1 goes to 3, then it's left alone. 3 goes to 1 to 2. 2 goes to 1. That. But if you do it the other way, 1 goes to 2, 2 goes to 3, 3 goes to 1, and it's different. This sparks, I think, kind of an obvious question. There's 2 groups of order 6, right? And they're different in some sense, right? One of them, order doesn't matter. One of them, order does matter. How many groups are there? This is actually one of the great problems in group theory that wasn't really solved till almost the 90s. This is classification. Well, there's some other technical things, but anyway, people wanted to understand it. It turns out you might say how many different groups, and I'm being very imprecise here. I'll be more precise, but how many different groups of order 2 are there? There's only 1. There's only 1 group of order 1. The identity, right? I don't care whether you call it 0 or 1, it does the same thing. Combine it with itself, it's a subgroup. There's exactly 1 group of order 2, 3, 5, 7, 3 prime, there's only 1 group. Order 6, there's 2. As the powers build up, it's worse. There are 5 groups of order 8. I think there's 14 of order 16, 51 of order 32. I think it's out of hand really quickly. But this is the first kind of example seeing the different kind of groups here. This theorem here is often called subgroup criterion. Let's let G be a group and H be a non-empty. So suppose G is a group and H is a non-empty subset. G, H is a subgroup. If and only no. This is actually a cool way to tell if a random subset is a subgroup, right? Well, assuming the subset is not it. It's a subgroup of G if and only if this happens. I'm going to prove half of this. These kind of things, like I said, this is called the subgroup criteria. But these kind of things, one direction is almost always easy, and the other direction is kind of where you get the meat. I'm going to do the easy direction as a warm up, and we'll do the hard one. Suppose H and G is a subgroup, and X, Y, H. Okay. Yes.
Contain the matrix or all of us.
Yes, it's a containment. It looks like an inequality sign because group theorists often use this kind of sign for subset. So, yeah. But I don't really care what you do. Suppose X, Y is in H. since H is a group, Y inverse needs to be in there. Right? We're assuming that H is a group, so if it contains an element, it has to contain its inverse, right? And since X and Y inverse are in H, then X, Y inverse is in H. And there's the forward direction. We'll talk about the other direction next time. Any questions? Oh, and don't forget, next time will be Wednesday. We have a review session starting at 5 o'clock, and it's in 105, not here. So that's a class in it until sometime. Anyway. Okay, any questions? All right, we will see you all on Wednesday.